Dear students, today we are going to discuss input and output characteristics of common emitter transistor. So we start with the basic. We have a two type of transistor, NPN and PNP. In the NPN, majority charge carriers are electron. In PNP, majority charge carriers are holes. So we will be preferring NPN in most of the application we have discussed in the theoretical section, right? So here you can see there is a three terminal emitter, base, collector. The area of the collector is more larger because the power will be dissipating in the only in the collector terminal. So that is the reason why area is large compared to the emitter as well as base. Okay, here compared to base, emitter is large. Compared to emitter, collector is large. You want to understand that part. Okay, this is a different type of transistor with a different packaging is mounted here. Okay, it was displayed here. You can see here. Okay, so like we'll go for a next slide. Okay, see here. This is a NPN and PNP transistor. This is for NPN and this is for PNP. This is back to back configuration for transistor. So we know that when you draw the transistor, so this is a N and this is a P and this is a N. So this N is a negative and P. Okay, so that is represent here. Again this P is sharing with this N also. So again another diode is sharing with your next thing. So I can represent like this can be represent like a one diode, right? This is a P and this is N. Again base is sharing, right? So PN, so that is why shown back to back diodes. So here you can see the arrow, why it is coming towards the emitter, because the hole which is moving from the base to emitter, so that's why the direction is given like this. When you go for a PNP, hole is moving from the emitter to base, that's why it is showing towards the base. Okay, there is a two junction, one is emitter base, another is a collector base. In amplifier, external biasing, always collector base will be reverse bias and emitter base will be forward bias. Okay, based on the movement of the charge carriers, it is broadly divided into three types. One is forward active, another is a cutoff or saturation. In the cutoff, both the bias will be in the reverse bias. In the forward active, both the junction will be forward bias. The saturation, emitter base will be forward bias and collector base will be reverse bias. Okay, this you have to understand before you are going for the configurations. Here, this is for NPN and this is for PNP. We are going to discuss only with the NPN. I'll start with the basic. Here emitter is grounded, input is base and collector is output terminal. See, base is input. That means the current which will produce here is only in the microamps. So that we can observe in the simulation part. Similarly, the current which is produced in the collector part will be large. It will be in the milliamps. That we can observe in the simulation part. So emitter will be ground. See, we can put a tabulation for more understanding. So that will give the clear picture. Okay, so I can write it as an input terminal and output terminal. This will be a voltage and this will be a current. So we will go for the input voltage. Input voltage will be VE and the input current will be IB, right? I hope this is understood, right? Similarly, when you go for output terminal, this will be VCE and output current will be IC. Okay, so this you want to do for the all configuration. So generally common emitter is a global configuration. I can change any configuration from this common emitter configuration part, like I can change to common base as well as common collector. Common emitter is mostly preferred because the voltage and current is moderate compared to other both will be large, so power also will be large compared to the both the configuration. Okay, that is the reason why the common emitter is preferred in the most of the application, and preferably we will be using the power amplifier section, right? So now we will go for the like a characteristics. See, I'll give very in-depth analysis when you go for the input characteristics. What is the parameter we have studied? We will make a tabulation again. See, this is the input and this is the output. Okay. So voltage and current. What is the input voltage? I hope you know VBE, and input current will be IB, and output voltage will be VCE, and output current will be IC. See, first I will give the information for input characteristics. Okay, first I want to measure the input characteristics. Okay, consider input current is IB and input voltage is VBE. Okay, so how you are going to see the input characteristics? Very simple. So this is a theoretical analysis. What you want to do is, I'm going to take a VCE for the different set of values. For example, I will be considering VCE as a 0, and I will be changing the VBE for different values of VBE. I will be plotting a IB current. Okay, that is a concept. That is, you can say like you will be finding a changes of IB with respect to the changes of your VBE when your VC is constant. That is a analysis you are doing. Okay, that you can find what is the input resistance from this graph. That will discuss in the next part. Okay, so here what I want to insist from this diagram is, when you keep a VC is 0, that is the output voltage. See, you know that emitter base is always forward bias. Internally, collector base is always a reverse bias. That you want to understand. So when you change a VCE like a 0, the depletion part, see, this is a emitter part, this is a base part, this is a collector part. Consider VCE is 0. So that means in the initial stage, so emitter, and this is a base and this is a collector. When VC is 0, the depletion will be very less. Okay, so when you change the VC, so that means your VCB also is indirectly it is affecting. So VC means indirectly it affecting the VCB also, right? So VCB will be increasing. So width of the base will be occupied by the depletion region. That means the area of the base is reducing. So now here very important here is, when you plot for VCE, your current, when you current will be like this. Okay, here you can, you know, it's just acting at a diode. So at exactly at 0.5 something it will start to produce, and current will be something like this when VC is 0. Suppose when I am increasing VC is 2, okay, that means VCB also increasing indirectly. So current which is producing here will be reduced. Why? That you want to know, because when VCE I am rising, indirectly it is affecting your VCB also. That means the area which is covering in the from the base part will be more, that with the depletion region, that is immobility charge carriers. That means the current which is moving from the emitter to the base will be reduced. That is a combination, the recombination will be reduced. So initially you consider like a 10 electrons will be combined with the base to produce a current. Okay, for this. When you consider the second case, because of the low area of the base, very few electrons is possible to combine in the base and current will be produced. Consider 6 holes are combined and corresponding current is plotted. So remaining electrons will be moving to the collector part. So the collector current will be processed with respect to the next part that we are not discussing. Here we are discussing the input part. So that is the reason why the current is reducing. I hope you understand. And when I am increasing VC is 4, similarly your VCB also it is impacted, right? So your current will be reduced. So here consider like a 2 holes only a recombination has been happened. So this is want to understand the change of base width is called base width modulation. It is modulating. What do you mean by modulating? It's change its width with respect to VCB or VCE voltage. So that is called base width modulation. Okay, that you want to understand the characteristics of the input part. Okay, so that is we have discussed in the already in theoretical part. See, now we will go for the characteristics. See, for more understanding, I have taken the screenshot of the LTSpice. Okay, so here what I have done, Like I have taken, I have plotted for only one value for understanding. I have taken only one value to get the exact input resistance. Please understand. Step 1, I want to find the input character. I want to find the input resistance. So what will be the aim? So aim of this experiment is to study the common emitter VA characteristics and to analyze the input and output resistance of the common emitter configuration. So this is your aim of your experiment. Okay, so what you can do is, first I am considering VCE is 0. Okay, that is I can take in as a VCE. I can customize. Okay, this is a part, this is a battery name, so I am taking this drop as a VCE is 0 first part. So I am plotting this current. Okay, so I want to measure what is your resistance. So I have taken the uh, two like I kept the two slot, right, traces. I have taken two and I kept here. Okay, I have taken two traces and kept it here. So one trace, it's saying like it is for first you can see this is a VB and this is your current. So I already said the current is in the base will be very small, it will be in the microamps. So that is very important, you want to understand. Another thing, when you see the horizontal part, so this will be a something 615 and this part will be something 636. So I think this will clear you how to calculate the input resistance. We will see in the simulation also. So when you see the vertical part, this will be like a 120 like a maximum 128 microns, and this will be a another part. So like this will be a current, this will be 58. Okay, so that you can see here. So this is a 120 something, this is a 58 approximately. So same I have plotted here. So this is a V2 and this is a V1. So this is I2 and this is I1. The difference I have plotted. So finally you are getting something 305.6 ohms. So see, this value may change based on the value you are taking. Typically it should be in the range of from 100 to 500, 600 something. So that is based on the value you are measuring. Okay. So formula is like a changes of VBV, changes of IB when VC is constant. So that you can analyze from this input graph. I hope you understood. Similarly, when you go for the output characteristics, what you want to do is, see, I want to find the output characteristics. What you want to do is, I want to find you want to change your VC. Okay, for that different current you have to plot when your current is constant. Okay, when your IB current is constant, I have plotted for different values of your current. Okay, so here in LTSpice you can keep your voltage as a constant. So with respect to the voltage, your IB term also will be constant. Okay, in the LTSpice. But theoretical part, we used to say changes of VC by changes of IC with respect to the different values of IB constant. So this is for each value of IB. Okay, so I want to measure the resistance, right? So I am taking only this step and I'm going to measure the output resistance. So you can see another, this is plotted in the milliamps and this is plotted in the voltage. So in the input, you can see it was in the microamps, here it was in the milliamps, because this is for IC and this is for VC. So I will go for the next part, that is here I have taken only one step and I am explaining how the output resistance is calculated. So I have taken the two cursor. So first we will see this is a voltage and this is a current. The current in the sense this is a IC and the voltage in the sense this is a VC. So I have taken the two value. The two value, this is your 10.017, this is the 7.991. So current, when you see the current, this current will be 4.231. So this part. Okay. This current will be like a 4.231 and this current will be something like a 4.1. Okay, so this is for 3 and this is for like a 4.4 and this is 3.5. okay, it's plotted for 0.5 amps difference. Okay, so when you define the difference, it was found to be like a 16771, that is 16 kilo ohm, 16.77 kilo ohm, roughly 16 kilo ohm. So you can see here, this is a 10 I have taken and 7 I have taken. So even you can take from this cursor value also. So So this will be the reverse of the resistance, right? Because it is plotting for this is a current and this is a V. So it is plotting for I versus V, but we are interested to find resistance. So you should take a reverse of this value. So this is another way. So that is 1.5900 into 10 to the power minus 5. If you calculate, the value will be 16 kilo ohm roughly. So this is a way you can solve for your assignment problem. Okay, so I hope you understood, right? So now I want to calculate the beta current. How you can calculate? So you can plot for a VCE versus IB, and similarly VC versus IC. Okay, you can take for one step, and you can divide this changes of this two value you can take. Okay, that is your output current by input current. So output current will be IC and input current will be IB. So I am written wrongly. So that is IC2 minus IC1 divided by IB2 minus IB1. So when you find, you can get what is your beta value. Okay, so that is you can look it. Okay, so this is a graph I explained. You can see for the different set of voltage it is plotted. So when VC is low, current is large. When VC was higher values, you can see the current was reducing because of the region which is occupied the depletion part. So this is a IC part, this is a VC part, this is a cutoff region, this is a linear region, this is your active region. So linear saturation region. See, this is only for very small amount of voltage it will be in the forward and forward both the junction. In this section only your emitter base and collector base both will be forward bias. In this section collector base and emitter base will be both will be for like a reverse bias, and the current we can see it is very less than microamp something. So that's why it is given in the highlighted in the gray color you can see here. So here you can see there is some resistance will be there. It is not a perfect flat, so there will be some changes of slope with respect to the VCE. There is a change in the ICE. Okay, so characteristics. Okay, see, I'm not going to draw the LTSpice like a circuit from the initial onwards. It's a very simple. I'll teach you first. Okay, see, first what I have done, I have taken one transistor. So like I have typed NPN transistor. So I have taken this transistor. Okay, I have taken this transistor and I have designed. Okay, so then what I have done, I have chosen some specific transistor. So preferably I choose like I going to the pick new transistor. I'm taking, you can see here. Okay, so 546, or you can choose 547B. Okay, so when you are designing you can choose 547B. Okay, so similarly you can fix this. Then I have fixed the input resistor in the input side and output the resistance in the output, like in the collector terminal and the base terminal. Okay, so I am named as R1 and named as R2. Here I fixed as a 2K and here I fixed as a 1 kilo ohm. Then I have taken the voltage source. So you know how to take voltage source, just type a voltage source. Okay, then you will be getting voltage source, right? So then similarly you can fix in the output side. Okay, see, I am going to find the input characteristics. Before that you can give the label net for this, because then only you can find easily. So you can take you can go here and fix the terminal here. Can just keep E, B, C. This are the label net, and this is a battery name. So you can keep it any name. This, for my understanding, it is connected to B. So I just given the battery name as VVB. Similarly, it was connected to the C. I can give this as VCC. Okay, it's up to you. There is no fixed name, only you have to give VVB. You can. It's up to your convenience. Okay, now I am going to find the input characteristics. What is the procedure? So I want to keep the output value different set of values, right, constant, and I want to change the VBE voltage. So for the VBE voltage I want to measure what is the current, right? That is the thing we want to find. So first I will explore this very important point, that is you just go to the edit simulation command. In the edit simulation command you can listen carefully. I have two sources, so first source and second source. The first source, when you want to find for input characteristics, you want to keep your input terminal, that is a battery name, that is a VBB, same name you have to give. See here I have given VBB, same I have given here VBB. The type of sweep is linear, source linear. Start value you can see here 0, 0 and 1, 1, that is a stop value. In between how it want to rise, like a step of 0.01, so it will plot. Then when you go for the second source, this is a VCC and it is a type of sweep is linear. See, you want to find for different set of values. So 0, 5, 10. So starting value is 0, the increment is 5. So I have plotted up to 10. That means you will be getting a 3 graphs. So 0, 5, 10. So that we will see now. I hope you understood, right? So I will explain again. The first source I kept the battery name, then linear, start value, stop value 0.01. So you can use same for your experiment. Okay, so not mandatory, this is a fixed one I have tried, you also can try. So you will be getting, if you change the value you will be getting different more increment, and you will when you change here also it will be plot for like a more set. So it's up to you, right? So I will be giving okay, then I will be saving this file and then I will run it. Okay, so I'll close it. This one I will open only the input graph. Okay, so I will save again and I will run. So when you run, see you got this empty graph. So what I want to do, listen carefully. So first you can see here, this is given for VBB. So you can look at the graph, you can look at the circuit, the emitter was grounded. So no way I can remove this emitter terminal. Okay, so for more exact measuring, so I can put like a VB, so capital B it will come. So I can put okay, so that's the reason why we want to give the label net for exact measure. So I just given VB and I want to plot add trace. I want to add the trace. What you want to measure? IB, right? So I'm selecting IB. So you got exact graph, right? You can see how the current was increasing for low voltage. This is for, see, I want to see for step, right? Go here, go to the like a view and see the steps. Okay, select step. See, it is plotted for 0, 5, 10. Suppose I want to see for 0 and select 0. Okay, see here when you select all are blue, when you select all will be selected. You can see all are selected in the blue line. Suppose I want to select for only one, you can select 0 and you can take for only one trace. So from this I can measure what is your resistance. Very simple. Okay, so this is a very simple way. So need not to keep a 3 steps. Okay, so very simple. Go to the view and in the select step you can select. So suppose I want to select 5, you can do it. So I have selected 0. So suppose I want to find what is the input resistance. What you have to do is you have to take a trace. So you have to take a cursor. So I have taken the 2 cursor. Okay, so one cursor I will keep here. So another cursor I will keep here. So in the PPT I have taken some different values. Okay, you can I have taken some approximately in this point, so you also can take it. Okay, so you can take exactly the slope. Okay, the slope you want to measure. So here only, see, you have a doubt why sir you want to select. The answer is exactly this is a point, it's changing from the off to on. In this is a point the current is rising linearly. So I want to measure the slope so that you can find what is the resistance accurately. So you can measure this changes of current and changes of voltage by the previous method what I said during the slides. Okay, so here for this value something you're getting like a 0.035. so once you take a 1 divided by 0.0035, you will be getting some resistance. Okay, so you can find the input resistance from this section. I hope you understood, right? So I have taken the 2 cursor and kept in the graph. Okay, so I hope you understood. Now we'll go for the output characteristics. Okay, so I'll open the output characteristics. So in the output characteristics, only thing you want to understand is I want to find a different value of IC for different values of VCE. So I will change the VC value. For the changes of VCE, you will be finding what is the current. Okay, during that condition your IB will be constant. Here I am keeping the input voltage as a constant for the different set of values. Okay, but theoretically we used to say the changes of current will be absorbed when you change your VCE for different value of input current. Okay, here the important thing is, so I will go to the edit simulation command. I will teach you, that is very important. You can observe the first source I'm keeping as a VCC because this is the first thing I'm changing. Okay, in the last input characteristic I kept a VBB, but here I'm keeping VCC because this is going to change. Okay, VCC linear and start value 0 to 20, increment 1. So that is given here. You can see here 0, 20, 1. So this is for that is the first source. That is in terms of output point. That is I am seeing the circuit from the right side. So when you look at the second source, that is VBB. The VBB is a linear, and see same value you can use in your finding. Okay, so need not to confuse with your class part. So you can take like a 500 millivolt and stop value 2000 millivolt you can take. So that is a 0.5. So that is given as a 500 millivolt same, and the increment is 100 millivolt. So if you give like this, you can measure the beta value very simple. You will not confused. Okay, that's why this value you can keep it as a fixed, or you can keep it as a more than this. Okay, so you'll be getting a easily. So this is for the first source, this is for first source, and second source 500 millivolt, 2000 millivolt and 100 millivolt. So you can see here, I will go okay, and I will save and I will run it. So when I am running, I can close the first part, that is the input characteristics, and I will take the output characteristics and save again and running. So see here, you want to plot for VCE, right, but it is showing for VCC. So I will interested to see only the VC, right? So I will change here. Okay, so VCC I have changed, and I want to measure only the like a IC current, right? So IC current I will select, so it is plotted, right? You can see here. So I will show in the graph. So you can see how the exact graph you are getting, right? So this is a graph you obtain, but it is plotted for different values. I want to measure output resistance, it will confuse more. So what I can do, go to the view and select step, and it is selected everything because it is displaying here, right? So I want to select only one value, so I select only 0.5. see, you got the only one trace, that is a one step. Now you can measure it very easily. So I go here and I'll take two cursor. Okay, so just click this. So two cursor you can take, first cursor and second cursor. So first cursor I will be keeping somewhere here and somewhere here. So somewhere here. Okay, so resistance of output will be something like it will be in kilo ohms. Okay, I said in the PPT, right? So here you can see, so this is a voltage range. So voltage range you can see, one is in the 12 point something on 3, approximately another value is 8. Okay, exactly 8.094, and current if you see, so this is a higher value is 5.57. so this is a value 5.57, another value is 5.25. so I want to find what is the difference of current by difference of voltage, right? So you are getting like a difference of voltage is 4.0416 and difference of current is 305.13 like a nanoamps. Okay, nanoamps. If you like a find a slope, you will be getting 7.595. so that is the reverse of the resistance. Okay, I have said during the PPT na? So same you can follow, and you can find the difference, and you can plot some output resistance. It will be in the kilo ohms. That is very important. You can do it. I hope you understood, right? So now suppose I want to find the beta. So how you can do it, I will teach you. So go to the add plot. Okay, you take a two graph. Okay, so then here I will add trace like a IC. So that is the output current. Okay, so then I want to add trace your IB also, right? So IB also. Okay, so here the current will be like a VC, the voltage will be VC, right? Capital. Okay, see, now you can measure it very easily, right? So here the current is coming in the reverse. See, we have to keep a IB. Okay, now you got it. So this will be, both are IB. It should be IC, right? So I will add the IC. Okay, this is a IB and this is IC. Okay, so what we can do is we can zoom it. Okay, now we can see. So I'll take a two cursor, first cursor and two cursor. So I'll keep the 2 point. So this is the difference of IB1 and IB2. Similarly, you can see difference of IC1 and IC2. So if you take a difference, you will get a beta value. So this is IC1, this is IC2. That is a difference. Similarly, you have a difference of IB1 and IB2. What is the beta? Beta is nothing but a changes of IC by changes of IB. So if you divide both the value, you will be getting the beta factor for this circuit design. Okay, I hope you understood. So in the this lecture I will explain what is the basics of common emitter configuration, how you have to calculate the input characteristics with the slide, then in the LTSpice how to calculate the output characteristics, then how to calculate the beta. Same you can do it here for this assignment. Okay.